As the title suggests, my talk is really Sigma 101. It's very basic. My apologies to those in the room and on the internet who will have seen or understand most of this already, but I think it's important that we start from a common understanding of what the basic principles are. I'm going to illustrate most of the talk, even though it's not necessarily relevant to this particular application, talking about sigma with respect to empirical equations, simply because it's easier to illustrate the point. So this will be where we begin with strong motion records of acceleration, pick off parameters like PGA, PGV, which are two of the NGA East parameters, or response spectra derived from various records with different spectral ordinates at different periods. Whatever parameter we choose, we take a large collection of strong motion recordings, we read the parameters off, and then we look for ways to relate those particular parameters, whichever is characterized in the record, to various parameters that characterize the source of the earthquake, the path to the site, and the nature of the site itself. And in developing empirical ground motion prediction equations, we generally will relate the logarithm of whichever is our chosen ground motion parameter, I call it y for illustrative purposes now, to these explanatory variables characterizing the earthquake source, as I said, the source to travel path site and the recording site, for which we'll generally now, as a default, at the minimum, use magnitude and style of faulting, the distance covering the path, plus, of course, the path is implicitly covered by the selection of which region we're developing our model for, and then the surface geomaterials or the nature of the site itself. And then we need to pick a functional form which relates the logarithm of the parameter of the ground motion parameter to these explanatory or predictor variables, which is magnitude, faulting, distance, and the site characteristics. And here's a typical example of a recent European equation, which they're becoming more and more complex. This is nothing compared to some of the NGA West equations, which don't get on one slide anymore, which is why I've used our own. And then, oversimplifying terribly the process, what's then done is we fit these functional forms to the data. This is an illustrative example for short period spectral ordinates. Across distance, we've got earthquakes of two different magnitudes, and the red and blue lines are the best fit, effectively, to the logarithm of those data, predicting, therefore, median values. But in effect, obviously, just from that picture, we can see that what's really happening is that that's just a representation of the best fit in a large dispersion or cloud of data. So if we look at any individual data point, like this one here, that's the observed value, and corresponding at the same distance and magnitude, we'll have a predicted value, and we characterize the difference between them as a residual delta. And the delta is therefore defined as the difference in the logarithms, which can be restated in that way. And the reason we do everything in logarithmic space is it's generally been found that these logarithmic residuals conform to a normal or Gaussian distribution, as you can see here. And so which is characterized by a standard deviation. And there's another parameter I've introduced here, epsilon. And epsilon is the number of standard deviations. In other words, it's a normalized residual. At any point, it's delta divided by sigma. And once we've assumed or say, shown it to be a Gaussian distribution, then where we are in terms of epsilon, how far or above we are below the curve, which is the best fit, has a probability attached to it. So if we have no epsilons, and those are on that curve, we have median values with a 50% probability being exceeded. The plus 1 epsilon, plus 1 sigma, is 16% probability or plus 84% if we go below 1 sigma. And the probability of exceeding the values decreases very rapidly as we add more epsilons, but the corresponding ground motion values also increase very rapidly because of the size of sigma, as we'll see shortly. So as I said, the logarithmic residuals are generally found to conform to a normal distribution with mean 0 and standard deviation sigma. And looking at any large data set, this is from the Abrahamson and Silver model at the early stages of the NGA project, their PGA values, without going into too much detail about what these axes actually mean, if you think of these as epsilon values, if the data is conforming to a normal distribution, then it will coincide very well with the red line, which is the theoretical distribution of a Gaussian distribution, and we can see they do so, at least out to 2.53 sigmas. This end, not so well, but this end doesn't really matter. These are the extremely small levels of motion that don't really concern us from a hazard perspective. So the distribution of the ground motion residuals, therefore, is completely characterized by the distribution of the logarithmic residuals, and therefore the logarithmic standard deviation sigma, which is what today is all about. So going back to this plot, we can say that the prediction at given magnitude and distance is not of an acceleration value or a velocity value, but it's a prediction of a distribution. It's a prediction of a probabilistic distribution of motions completely characterized by sigma. And just as an aide-memoire, we can think of this, rather than a Greek letter, as being an acronym for scattering ground motion attenuation. So representing it alternatively like this, our logarithmic value of the ground motion value is a function of the predictor variables plus delta, or a function of those same explanatory variables plus epsilon times sigma. In other words, the normalized residual multiplied by the actual sigma value. And we can see here that it's not something we've invented. It's a real characteristic of the data. Any empirical data set we look at, however well it's been prepared in terms of metadata and record processing, will have this very large scatter that sigma represents. These red dots are the soil site recordings of the Parkfield earthquake of 2004, and they're being compared with the Bohr, Joyner, and Fumal equation of 1997, median values +1 and +2 sigma. So that's epsilon values of 0, 1, and 2. And we can see there are data points outside the +2 and -2 epsilon. The scatter is large and it's genuine. So if you were to focus on the first 10 kilometers from the fault, we can see values from just over 2G to about 0.08 G on the same, at comparable distances from the same earthquake source and on comparable sites. This just seems to be the inherently variable or random nature of earthquake ground motions. The values of sigma we get, it will partly depend in a small extent on how we treat the records in the first place. Real accelegrams are usually triaxial with 2 horizontal and 1 vertical component, and there are several different ways of treating the 2 horizontal components, although the standard practice is becoming, or at least in the US has become, the geometric mean of the 2 horizontals, but other definitions are used, and other definitions lead to different sigma values. So we have calculated here ratios of sigma values for all sorts of different other definitions of the horizontal component with respect to the geometric mean. The differences aren't large. In many cases, it's 5% for most of the ones which are considered to be broadly equivalent to the geometric mean, but values up as much as 10% larger are sometimes found with other definitions. And even though 5% doesn't sound a lot, if we can add or take off 5% to sigma, it can have a significant impact. This plot shows sigma values for PGA, given in natural log here and log 10 there. The conversion is obviously that, against the date at which the empirical equations were published, back from 1970 to the most recent models, which are primarily the NGA. And you can see the values are fairly large, and most importantly, they're not getting any smaller with time. The majority of them lie within a certain range, and we typically find the values to lie there. We're surprised if they could be if they come out much lower, and disappointed if they come out much higher. And this is despite the fact that sigma hasn't decreased significantly over all that time, is despite the fact that we've gone from having about 300 records to work with 30 years ago to having closer to 3,000 strong motion records from shallow crustal regions at our disposal today. And just to show here, this plot shows exactly the same thing. On the left is for engineers in linear axis, and on the right for seismology on logarithmic axis, seismologists. And they're showing median values for a given magnitude and soil type and the plus and minus 1 standard deviation, just to convey just how, let's say, large is the distribution, how wide is the distribution of our predicted motions. And remember that a lot of the data, 30% of our future observations for this earthquake would lie outside the broad blue band. And as you see from the sigma values from the previous slide, the 84 percentile PGA values, those are the median plus 1 standard deviation, are generally more than 80% larger than the median. So the sigma values are having a very significant effect. And we see that very directly if we were to do deterministic seismic hazard analysis, where we take individual controlling earthquake scenarios and then simply calculate the resulting motion at the site from putting the maximum earthquake at the closest possible distance. Practice amongst those who still use deterministic analysis has generally tended towards using the 84th percentile motion rather than the median. And of course, there it's going to be very much governed how far they're going to be above the median. It's going to be totally controlled by the value of sigma. If you are going to do that for a single deterministically chosen scenario, it doesn't necessarily make a great deal of sense to say, I'll take 1 standard deviation. It would possibly be a more rational approach, since we are talking at that stage about a probabilistic distribution, regardless of whether our philosophy is probabilistic or deterministic. A more rational way might be to say, I've chosen my earthquake scenario in terms of magnitude and location. Let me choose the epsilon value so that it corresponds to a probability of exceedance that I'm comfortable with. And if we wanted a conditional probability of exceedance of 0.1, it would give us 1.2 epsilons, 1.28 epsilons, rather than the 1 that's normally added. And so on, if we go down to smaller and smaller probabilities, we add more and more epsilons, and we'd get some incredibly large ground motions. So you still then need to have some rational basis for how will I choose this probability of exceedance, and the only rational way to do that would be to take into account the rate or frequency of the earthquake scenario you're attaching this to, in which case you've come full circle. You're doing the basic elements of a probabilistic analysis, and you may as well go full hog. So I'm now going to illustrate the impact of sigma on PSHA, which doesn't consider a single scenario and earthquake scenario, but considers all possible scenarios, and not only all magnitudes at all relevant locations, but also all possible values of epsilon as well. So it considers the full distribution of those 3 variables that control the ground motion. And in the next 3 slides, for those who, I imagine no one in the room, but maybe other people watching will benefit from this, the basic essence of PSHA is we start by defining source zones, exactly what has happened in the project Larry has just described. And each of those source zones is characterized in terms of a seismicity model, usually a Gutenberg-Richter relationship, or some other if it's a single source. And that can be translated into annual rates of earthquakes of different magnitude. And the process of PSHA is then simply an integration of the contributions from all possible earthquake scenarios. And we do that by taking each source and breaking it up into elements. And if I'm just illustrating all of this for single elements, obviously the integration would have to be over all of them. So I choose this site, this sub-source here, and I can calculate how far it is from the source. Then I choose which magnitude I'm going to consider right now. It just came in there, the darker block. And then I've got my prediction equation. And we're going to do all these calculations for a target acceleration, in this case 0.3 g. So I can now, for that magnitude, take my median ground motion prediction. I've got my distance here, so I can calculate that. And I see where I am. And it turns out, fortuitously, that in this particular case, I'm bang on target. I've hit the right acceleration, so I'm done. But for my next scenario, I'm going to choose here a smaller magnitude instead, this one here, which happens more frequently, but is smaller. So consequently, the predicted median motions are going to be lower. So at the same distance, I now fall short of the target acceleration, and the only way for me to predict the target 0.3 g at the site is to add on some epsilon to get it up, get the motion up to the right level, which means I'll have a less frequent motion because I now have a value of from the distribution which is going to be exceeded less frequently, but I'm back onto the 0.3g. To finish the illustration, let's move now to another sub-source somewhere else, a bit further away. So now we have a longer value of distance. Let's maintain the same magnitude. So the curve is still the same. And now, because we're at a further distance, we've again fallen short of the target acceleration. So I need to add even more epsilon to get up there. So if I now summarize in the next slide what I've done, I've defined just 3 scenarios of the several thousand that would go into a real hazard calculation. The first was at short distance, large magnitude, I needed no epsilons. The second was at the same distance but a smaller earthquake, I needed 1 epsilon. And then I went further away at the same magnitude, I needed 2 epsilons. And then I calculate the frequency of the earthquakes and the exceedance. So the frequency of the earthquakes, here it's low because it's a large magnitude earthquake. It'll be about 10 times more frequent for the smaller magnitudes, and that's maintained. But each time I went to a higher epsilon value, I got a smaller probability of exceedance. So for those scenarios, the probability of exceeding the target ground motion in each case will be the product of these 2 frequencies. I've got those 3 frequencies. These are independent, so I can simply add them. And a PSHA simply integrates over all those subsources, over all the possible magnitudes from the minimum we consider up to the maximum considered feasible, and I consider the full range of epsilon values. And the result is we end up with a seismic hazard curve showing annual probability or frequency of exceedance against whatever ground motion parameter we happen to be looking at. If we don't include sigma, which is still frequently done, then we get hazard curves which look like this. And at around this point in the calculation, what happened was they took the largest magnitude to the edge of the closest seismic source, and they couldn't make things any worse. So the hazard begins to saturate. In very simple terms, that's a PSHA curve, and this is not PSHA. It's dying out, the practice of doing PSHA, sigma-less PSHA, but it's still not entirely eradicated. And of more concern is we're now going back in nuclear sites around the world and reassessing the hazard where 20, 30 years ago it was calculated without sigma, and getting some, they shouldn't be surprises, but they are for the people who own those plants. Just to put it in perspective, up until 1988, the USGS was calculating hazard in this way. So the message of sigma must be included every time by all people has taken its time to filter through. Once we accept that sigma's got to be in there for it to be PSHA, we then see that the value of sigma has a very large impact. So this is for a site in California. And we've calculated hazard, keeping everything the same. 0.23g is the published PGA sigma in log 10. And we've just calculated how the hazard would change were the sigma value to be slightly higher or slightly lower. And you can see as we increase sigma, we get hazard curves that bend off to the right much more rapidly and result in much higher ground motions for any given annual frequency of exceedance. So seeing that, since we have to include sigma, and large sigma values have a big impact on hazard, the next logical question would be, well, can we reduce the impact of sigma? Can we just cut it? If we truncate the sigma, which basically means when I do those calculations, if I ever need a sigma value which is an epsilon value above my truncation level, I simply ignore that scenario and don't include it. You can see from this example that this is with using only median values, non-PSHA, truncating at 1, 2, 3, 4, and 5 sigmas. To make any real impact on the hazard, you have to truncate quite low, 3 or 4. This is for a fairly low seismicity region. We'd have to be saying we're not going to ever consider scenarios with epsilon greater than 3 if it's going to really have any benefit for us in terms of reduced hazard. This is an example that Norm gave us from the Bay Bridge. Higher seismicity, and you can see that to really impact there, you need to truncate even lower values to have a real impact. The problem is there is no current justification, physical or statistical, for truncating anywhere below 3 sigma. Here we've got from one of the NGA equations, I believe it's the Abrahamson-Silver equation again, at various response periods, the distribution of the residuals normalized into epsilon values compared to the normal distribution, which is the dashed line. And we see again, not only does it conform to the log normal distribution as assumed, but more importantly, is the maximum residual is always above 3, and it's very often close to 4 epsilons. And that's in there in the data, and we've examined those high epsilon values, and they can't be assigned to any particular physical cause, and therefore we can't remove them from the model. So in a 2006 study for EPRI, which is going to be referred to today for other reasons, it was concluded that there is no basis currently to truncate the ground motion distribution at less than 3 sigmas. So truncating sigma isn't a way out in the near future. But to discuss what we're going to do with sigma, we need to maybe discuss it a little more and characterize it. And the first thing to talk about is the nature of what it is. It's an aleatory variability. That means it basically represents randomness. The word aleatory comes from the Latin for dice. But it's actually apparent randomness with respect to a given ground motion model. Because we talk about sigma being irreducible, which it is in a sense, but only with respect to the model to which it's associated. So, and that's the problem, is we have very simple or even crude models for what is a very complex process. And the biggest single contribution to sigma in these empirical equations is actually the absence of the parameters that influence the ground motion but are not included in the prediction equations currently. So, for example, we characterize the source size by magnitude, but everything else, stress drop, directivity, asperity size, is not included in the models. In terms of the site geology, we can use, in the better models these days, shear wave velocity over 30 meters, VS30, to characterize the site effect, but we don't really consider the deeper VS structure. And even when we do have these good parameters, there's still an approximation for, in all cases, a wide variation. Take here 2 sites. I'm showing them both down to 80 meters, the geological profile, the stratigraphy, very different. One from LA, one from Haifa in Israel. If we look at their shear wave velocity profiles, they're quite different, but when you calculate the VS30 values, they're almost identical. They definitely fall into the same NIHERB class, and if we put these values into any predictive equation, they tell us there's no discernible difference in the site response between the 2 sites. But because the layering and the velocities of the relative layers are very different, when we calculate using nonlinear analysis, large suite of records, the actual transfer function of the sites, they're, as we'd expect, significantly different. And using these simple parameters in our models doesn't capture that kind of variability within the observations from that site class. So if this is the difference between the amplifying effect of 2 sites with the same VS30, putting VS30 into the model will not get rid of the variability that represents the difference between them. Unless the data is very well distributed, we're always going to have uncertainty about where we are. And that leads us to another type of variability, and that's on top. This is different from the sigma now. We're moving into another part of the problem at this stage. The blue line here are NGA predictions, median values. The black lines are not part of the equation. They're an attempt just to illustrate the concept of the uncertainty that where these equations are less well constrained. This is for magnitudes between 6.2 and 6.8, which are pretty dense, around 6.8, and we have a handful of records at shorter distances. So we can actually say that the median is very well constrained down here, but somewhat less so as we come into the near source region. For larger magnitudes above 7, the data is good to constrain the median values way out, but as we come in at less than 10 kilometers from the source for this particular site class, we have no records and no constraints. So if we think of these as kind of confidence intervals, then they have to start widening out very considerably. And that's what we refer to as epistemic uncertainty, and it basically reflects our lack of knowledge, and in this case, lack of data to constrain the model. Epistemic comes from the Greek for knowledge, as you can see here. So epistemic uncertainty in ground motion prediction equations is generally handled by using more than one model, as is being done in the USGS hazard maps, for example, in a logic tree with weights on each of the branches that reflects the relative confidence of the analyst in each of the models, and that's very often equal weighting, in some case like using the NGA equations. And whereas the influence of the aleatory variability, sigma, is to change the shape of the hazard curve, what consideration of epistemic uncertainty does is give us multiple hazard curves, which is quite different. So we'll end up, this is the one part of the logic tree used for the latest USGS hazard maps. The ground motion models are the final part of the equation here. And you can see you've got 3 of the NGA models there, assigned equal weights, and the calculations include using each of them in turn and then weighting the results by the weights on those branches. And when we do a hazards PSHA in a logic tree framework, we end up with not just a single hazard curve now, but a whole range of fractals of the hazard, the median and the higher fractals, and the spread of these is it tells us how much epistemic uncertainty there's in there. And in the nuclear industry and other places, the practice is actually then to use the mean hazard at any ground motion, which tends to track across the fractals as you go to lower and lower annual frequencies of exceedance. So coming back to the question of why is there epistemic uncertainty in ground motion predictions, these are the 5 NGA equations compared at magnitude 7 at a given distance where the data is sufficiently dense that they agree fairly closely. This is for strike-slip earthquakes, which are the most well represented. At magnitude 6, it's still fairly good. At magnitude 5, the data is actually less rich because there are less records down there. It wasn't well populated, and we see that the equations start to diverge somewhat. And when you go up to magnitude 8, equally, you're going beyond the limits of where the data was present in the data set, and we start to see some divergence amongst the median predictions. But in addition to having epistemic uncertainty in the median predictions, we have to also take into account that there can be epistemic uncertainty in the aleatory variability. In other words, the median value of ground motion predictions has epistemic uncertainty, so do the associated sigma values. And the best way to illustrate, I think, why there's an example of epistemic uncertainty concerning sigma on ground motion predictions is the difference between those models which are heteroscedastic or homoscedastic, which means that they include or don't include a magnitude dependence in the sigma model. These are the NGA models. You can see they don't agree on this issue. These are their sigma values against magnitude for PGA 1-second response. 2 of the models are homoscedastic. The sigma stays always the same with magnitude. The others find a variation with magnitude, which they then truncate to keep constant at higher and lower values. Similar things have seen in the previous generation of equations. All of these equations have magnitude dependence, and most of them, when they get to the higher values, assume sigma then remains constant, and similarly, they don't let it continue to grow at lower values. The 2 I've highlighted in black here are European equations, and they have a very pronounced magnitude dependence of sigma. They also have higher sigma values in general, which tells us something about the nature of our database. But they also didn't make any assumptions about what happens beyond the limits of the data. So we just see this very pronounced inclination here. And this is how we find it. We used something called pure error analysis. We bin the data. And you see here our standard, we find there is an apparent decrease in the sigma value as, excuse me, apparent decrease in the sigma values as we go across to higher magnitudes. But the fact is we've since found that it's very sensitive to which binning value how we bin the data in terms of magnitude and distance groups. It's also not statistically, the slope of that line there is not statistically significant for many of those bins. And we also have suspicions that down here at magnitude 3 and 4, some of that variability is coming from the fact that we don't have very well determined magnitudes and perhaps other parameters. And up here at the larger magnitudes, we actually don't have a great deal of data. So we can't necessarily conclude that it's a genuine feature. And when we've recently been forced to go back and look at the nature of our equation, and this afternoon Frank Sherban will show you why we did that, and looked at the sigma values, and log 10 for for 4 different magnitudes here across the period range, you can see we got some really bizarre values. The dependence is way too strong and unconstrained, and we have sigma values of 0.8 here, which are essentially unusable. You can't start running PSHA with those kind of values. As a result of which, we've just, coming out next month, revised equations using exactly the same data set, but we've played it safe this time and gone back to a homoscedastic model, and we now have kind of sigma values that don't look crazy and we can live with and we can happily recommend people use. But it is uncertain whether that's, let's say it's undecided. There's no, if the fact that 3 of the NGA models do have magnitude-dependent sigma, 2 don't, we no longer do, the jury's still out. It's not something that's been definitively resolved. So when we set up a logic tree for the ground motion part of an input to a PSHA, we'll have various branches for the median predictions with their different equations with their assigned weights. And for any one of those, we may decide, for one or all of them, to add additional branches to recognize the fact that we'd have uncertainty in what the sigma should be. And this could be the original sigma from the equation. We might do a homoscedastic or hetero, depending on which was used, and some other modifications. So we can set the logic tree up in this way. This is perfectly legitimate. And it also enables me to illustrate another concept, which is potentially very confusing, is that the way this is sometimes done is not to represent these parts of the logic tree with discrete branches, but instead with distributions. And this is what was done, for example, in the Yucca Mountain study. So they represent the distribution of predicted median motions, for which you first have to put these models into some increasing order of predicted median, and they give that distribution, characterize that distribution by sigma mu. And similarly, you can do the same for the distribution represented by the branches on sigma and get sigma, sigma. And I've put this figure in mainly to illustrate what these concepts mean, because in talking about sigma, we're mainly talking about this sigma. And I believe for those, as you come into this subject, sigma mu and sigma, sigma, and dare I say it, there is sigma, 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 it gets pretty confusing very quickly. So hopefully this at least illustrates what the basic concept is. Coming back to the sigma, the real sigma, can we reduce it? And in theory, we can't. It's inherent randomness. By definition, it's irreducible. But as I said, it's with respect to a model. It's the apparent randomness left after you've derived a model to explain the nature you've observed. Therefore, better models, which better explain nature, should reduce sigma. And a lot of what's been done in the last 20 years in ground motion modeling, or 30 years perhaps, has been aimed at doing exactly that. So we add additional explanatory variables. Our earliest models had just magnitude and distance. What we've included since has included, for example, style of faulting. So this is from the European equation. You can see the residuals organized by normal, reverse, and strike slip. And the large line there, in each case, is the mean value of all those residuals. And you can see that that red block represents the difference in the mean of the reverse compared to the strike slip. Taking that difference out will reduce sigma, but by a tiny amount compared to the overall spread of the residuals. So we get something, but we don't get a lot. Similarly, for including and refining the way we represent soil types, which goes back to the case of the 2 comparable sites I showed earlier. These are slides from Dave Bohr, showing residuals from his previous equation when the data were classified, grouped by Nieherb classes, and then by continuous VS values. And if we look at the resulting sigma values, leaving site class out of the equation at all for PGA gives a 0.25 on log 10, which means that 84 percentiles are 80% bigger than the medians. By going all the way through to VS30, it's down to 0.2, and they're only 60% bigger at the 84% than the median. In terms of the intermediate steps, Going to rock-soil distinction rather than nothing actually would have brought you no gain. Going to the NEHRP classes actually gets you almost as far as you get by going beyond to continuous VS. So we can spend a lot of time trying to make our models more sophisticated, but if that's what we're doing to get sigma small, we're probably on a losing battle. There's a law of rapidly diminishing returns. And we can see that going back to this, sigma isn't getting any smaller or significantly smaller over time. And that's despite the fact that our models have become horrendously complicated. These are the number of coefficients in the published equations against the day. Nice, sober equations in the early days, just 3 straight coefficients, or 4 or 5 for the very adventurous. Now we get values up to in the 70s. But ignoring that, this is an equation which has a coefficient for every individual station. But equations now routinely have 10 to 20. All the NGA equations have about 20 or more coefficients. Doing that hasn't reduced sigma appreciably. So that's not the way we're going to end up with very small sigma values. There are other ways to reduce sigma. An imaginative way in Italy was you took the data set. This is the data they used, and that's the medians, and this is looking at the residuals. These are the plus or minus 1 standard deviation. We went back and just included the records from the same earthquakes they analyzed, but used all the records rather than the ones they'd selected. And lo and behold, lots of the ones they dropped were the ones that would have made their sigma significantly larger. So you can get sigma by very selective data selection, but obviously that's neither very scientific nor very robust. So that's not going to be an option either. In his recently given distinguished lecture for the ERI, Norm gave this in London a couple of weeks, and characteristically put it very succinctly, and I think very well. As our knowledge of the generation and propagation of earthquake ground motion improves, and of course as we get more data, we will reduce epistemic uncertainty. Epistemic uncertainty is lack of knowledge. So you get more knowledge, you've got to reduce it. What will happen to aleatory variabilities will be refined. It cannot be reduced, but it will be refined. And what that really means is that we need to decompose sigma into all the parts that contribute to it and analyze each part. And some of them we may find are not as random as they appear to be. Some of the elements of sigma may actually be transportable or transferable to epistemic uncertainty, at which point we can, in the first instance, put it into the logic tree, and in the longer term, get data or models which will reduce that epistemic component. To get there, we first need to break things up. I changed this slide last night so that we're all using the same terminology. We're going to talk about different types of residuals. This is the median value of an equation. The red one here is the median value if I'd only used that cluster of all the red diamonds there are from a single earthquake. And there's what we call an event term or an inter-event residual, eta 1, which is how far the average ground motions in that event were from the median. In other words, this was a high stress drop or a highly energetic event. Similarly, the blue stars or crosses are from another event. They have a lower median and a negative eta 2, showing that it was a less than average event in terms of energy or stress drop. These are inter-event residuals. Then within of each of those, we have the intra-event residuals. How far was any individual observation from the average for that particular event? And it's very useful. And similarly here, we have, you can calculate for any of them, but the illustration of an intra-event residual for event number 2. And it's very useful to break it down into these two components. And now, to confuse things more, we'll call what we've called up until now sigma, we'll clarify with the T that it's the total sigma. It's the total variability made up of two components, tau and sigma, where tau is now the inter-event variability, which is earthquake to earthquake. In other words, how different is one magnitude 6 reverse faulting earthquake from another magnitude 6 reverse faulting earthquake, when we have nothing else in the model to tell us about the nature of the source. And sigma now, this sigma here, is the standard deviation of the intra-event residuals, and effectively it's the record-to-record variability, and we can think of that in the simplest terms as the spatial variability of ground shaking. Here are typical values from our revised European equation. That's our total sigmas as a function of period. The larger of the two components tends to be the intra-event sigma, tends to be the biggest contributor to total sigma, is the spatial variability, but there's an appreciable contribution coming from the inter-event variability as well. We can also break down the aleatory variability into modeling and parametric components. This is an updated version of the table we're all very familiar with from Toro et al. The parametric variability effectively means the propagated effect of the variability in the parameters in the model itself. So, for example, if we have the systematic variability errors in the determination of magnitudes, distances, depths, etc., if we can quantify those, we can effectively unpropagate them and subtract them from the total variability in the models, the contribution of the parametric aleatory variability. And that's been done, for example, in the Abrahamson and Silva NGA model for magnitude and for depth. But you can see the red and the green are the ones to compare in each case. It will get us something, but like everything else we do, which is this tweaking, it will get us something modest. But given how important sigma is, even modest reductions are worth obtaining. The fundamental problem, we believe, with sigma is what's called the ergodic assumption, which basically means that what we're aiming for in PSHA is what will be the variation in ground motions at a particular site over time. We haven't got thousands of years to wait and see what that will be, so we substitute the variability over time at one location with the variability over many locations in a given time, the period of observation we have, which is at most a few decades. So we take records from several sites, and in some cases several regions or several countries, and we derive equations where the variability represents the variability amongst all those events and stations, and we use that as a surrogate for the variability of what would happen at an individual location. We trade space for time. Now, if you look at single station sigma, that basically means you take repeated recordings at a single location, many, many earthquakes at one site, and we can now finally do this because there are enough sites around the world starting to have a sufficiently large number of recordings to allow some statistics to be done. We can look at what the variability at an individual site may be. Gail Atkinson published something to do along these lines 4 years ago using shape map reports from the LA basin, and she found on average that if she calculated the sigma values at individual stations, they were 10% smaller. So you can see the reductions she's finding here for PGA, PGV, spectral ordnance. And it varies from parameter to parameter, and of course from site to site, but she did illustrate a systematic reduction in the total variability when we're looking at individual sites. The next step up from that, obviously, is to go to single combinations of source and site. In other words, single path sigmas, where we're now sampling only the variability of events and at one source along the same path and at the same site. And for the LA basin case, Atkinson found that reductions of up to 40% of sigma could be achieved doing that, when she was combining records from a single station, but only records generated by earthquakes in a single source. And other studies have begun to appear with even more dramatic reductions. This is from a study of the KICNet and KNet data in Japan, and you can see very significant reductions in their sigma values. And these are really encouraging, because these are bigger than we've seen with all the other things we've tried to do with more complex models and extracting parametric variability, etc., etc. Another study has just been, it's in press, or under review, using data from Taiwan, which Norm and colleagues have prepared, using the green, it looks green here because this is all the travel paths connecting stations and earthquakes. The stations are the red and the earthquakes epicenters are the blue. And they've done both single station sigma using those recordings, but then also taking clusters of earthquakes, and where they are looking at just those single effective source area and the single path site combinations for different groups of the recordings. And this table from that forthcoming paper summarizes for these different regions total sigmas single site sigmas and single path and site sigmas. And the values, when you do this removal, effectively, of the ergodic assumption, start to be surprisingly stable, about 0.6 on natural logarithmic values here, and of the order of 0.4 on natural logarithm there. These are really much smaller than we would have hoped for in the past. This could be a very big step forward. The problem is we can't just reduce our sigma values by these amounts. We can't simply say, I've got less variability, and therefore I can get rid of it, because it assumes we know what the average, the median motion is, either for that site, in other words, what's the characteristic site effect, or what's the median ground motion for earthquakes coming from this source being recorded at that site. If we don't know it, then we have to pay a penalty for reducing the sigma by adding branches to our logic tree to represent the epistemic uncertainty in not knowing those median values. I tried to illustrate it with this plot. It's a trade-off. If you like, the red is the broad, large sigma distribution from our whole data set. Any individual site or source site combination is going to have a narrower distribution with a smaller sigma. But I can only invoke that smaller sigma if I know where its median is with respect to the overall median. For single sites, there may be ways we can do this, as Norm's about to explain. And in the long run, it may be possible to do it for source and site combinations as well. But we can't just start reducing sigma values by 10% or 40% today without paying a penalty. To finish, because what I've been talking about now is almost entirely on empirical and ground motion equations, we have to talk about simulations and the irreducible variability in stochastic and other types of models, because that's what's going to be mostly used in the NGA East. And we can't simply get sigma now by calculating the distributions of residuals. We have to look instead at the variability of the various parameters that go into the models and their correlations, so that we don't overestimate how variable things could be, plus misfit of models to observation to reflect the inference of parameters not included. And again, here, it can be very useful to distinguish between modeling uncertainty and parametric uncertainty. It becomes really particularly useful into this case, and then to break them down into aleatory and epistemic. And I'm not going to dwell on this too long, because it's this very famous table from the Toro et al. 97 paper, which I think you're all familiar with, and seen from the perspective of the seismic hazard analyst and from the ground motion analyst. So coming in from this side and looking at parametric uncertainty, I'm going to focus on this part of the table, make it a bit clearer there. Aleatory parametric uncertainty. For example, what's the variability of stress drops in the central and eastern United States? For a given magnitude class, what's the distribution of sigma values on future earthquakes? But the epistemic parametric uncertainty is what's the median stress drop and the variability of that median for central and eastern United States earthquakes. These are the two things that have to be determined simultaneously to get the parametric uncertainty in the model. That was what was done, and an adaptation of this framework maybe will be what we used in the NGA East endeavor. But remember, we're trying to get these values here for events that have never been seen or measured. So then we add the aleatory parametric uncertainty in all the parameters, plus the aleatory modeling uncertainty, together with the epistemic uncertainty, and that's how the total uncertainty model was built up in the Toro et al. Study. That's one way to do it, and modifications of their approach could be adopted. Something does need to be done. This is from the EPRI 2004 report. It's an illustration of sigma in effect. It's the epistemic uncertainty on sigmas for central and eastern United States ground motions. These are all the models here, and these are their sigma values against magnitude, mostly homoscedastic, some heteroscedastic models, but an enormous variation. And recalling the impact that sigma can have on that, or does have, on the hazard calculations, there needs to be some resolution of this, or maybe it cannot be resolved, maybe it can't reduce at this stage, but it needs to be well characterized as part of the output of the NGA East project. So, in my concluding remarks, points to emphasize, firstly, what we basically essentially meaning by sigma is the aleatory variability in ground motion predictions, even though, as we've seen, it can be more refined than that. It's part and parcel of a ground motion prediction. The median prediction alone is, I wouldn't say meaningless, but it's not the full representation. We predict distributions of ground motion, not deterministic values. We can't wish sigma away, and I think most people now accept that. It's always got to be taken into account, and it has a very strong impact on PSHA. You could probably argue that it has a dominant aspect, influence in many senses. Truncating sigma isn't going to help us because it's not feasible at the current time at a level which will actually get us any real benefit in terms of hazard results. So the most promising way forward is try to analyze sigma, break it down into its component parts, and identify which of those may be epistemic in so much that they can be determined rather than left as random, and then subtracted from the total sigma. And that's really the big challenge. And by way of illustration, this is Norm in London a couple of weeks ago trying to do it for the Pegasus project, and he's about to redo it for you. He was very pleased with what he did. With the rest of us, barely understood it, but I hope today it'll be a little clearer. That's the end of mine. Thank you.
Thank you very much. Thank you very much. Very interesting, informative presentation. We have few minutes for questions. If you have any questions from Julian, just a second. You have to use this because it's recorded.
Thank you. At the beginning of your presentation, you mentioned that current attenuation relationships are extremely complicated, and some of them you need the whole page to see this formula. And as a result, you don't still see huge decrease in sigma. Now my question is kind of philosophical. Is it the right way to go to make such complex and not physically related to anything formula? Is it the right way? Is it the right approach? Are we going in the right direction with this if we don't decrease sigma and make our empirical relations so complex and so far from kind of physics that we know?
Okay. That's a complex question. I mean, they're still simple compared to the physics of what's actually the processes they're trying to represent, number one. I don't think it would be fair to say that the NGA models are unphysical. I think a great deal of physical reasoning has gone into developing the models, deciding which parameters to include, to analyze the influence of some of those parameters, and in some cases to do additional modeling of those effects, like nonlinear soil effects, embedment of faults, etc., etc. They're not. It's not purely a statistical exercise. It is transferring aleatory variability into epistemic uncertainty on the values of those explanatory variables in future earthquakes. That must be the right way to go. My personal opinion, and perhaps Norm will have to comment, he may disagree, is that some of the NGA equations have tried perhaps to go too far, that they tried to squeeze more out of it. My reason for being concerned about that is if a future earthquake produces very different ground motions, the equations may suddenly change again to track whatever is the new observation. And it is a fact the NGA West equations are being used in coastal California, and the amplitudes and aleatory variability at magnitude 7.5 is constrained from earthquakes in Turkey, Taiwan, and Iran. And we don't yet know what the ground motion distribution will look like on a magnitude 7.5 earthquake in California. For the NGA modelers, I presume they hope it will look like those other countries.
All right.
Thank you. Thank you.
Comments?
This is almost a different topic, so I'm going to answer this very quickly. the NGA models were not about statistical fits to empirical data. The whole concept was to start to use numerical modeling to constrain how the model scaled beyond where we have data. The complexity that you get in those equations is what you take if you took a bunch of simulations and now you try to parameterize that. So you shouldn't be looking at the number of data points that we have to constrain that effect. It's what numerical simulation, physical models, were the basis of how we do that. Okay? And that's really a very different way to go about ground motion models. That's why this thing was actually called a next generation. It's supposed to fill in between purely empirical models and a move to purely use of simulation. And in trying to find an equation that works to capture all of the complexities you get out of a numerical simulation, you're forced to have all sorts of smoothing tapers and things like that. That's what drove the complexity. So you shouldn't think about it. We weren't driven by sigma at all. A lot of what Julian said is right. We gave up on trying to add parameters to reduce sigma. We added parameters to try to fit the way we thought the model scaled. And building ground motion models is not handing this off to a statistician. We're model building. You have to have some idea of the physical process. Most of what we're interested is outside the range of where we have much constraints. And so that's really what this is all about.
Great. One more question.
Yes. Well, first, I really should compliment you on a fantastically wonderful lecture. It was
Thank you so much.
very well put and very well explained. My comment is really regarding the constraint on number of sigmas we should use in the probabilistic analysis. And while what you showed us was perfectly correct as far as statistics go, if we look at the physics of the problem, and the reason for suggesting some 30-odd years ago that we should limit that number of sigmas, is when we get to the larger values of acceleration or spectral values. Because physically, we should be seeing a lot more damage than suggested by the data. So my suggestion or question to you, have you really investigated that trend, not in terms of the entire data set going from less than 1% G all the way to whatever number you used, but strictly on those really large numbers, and see maybe there is a deviation there, which might then invoke that maybe we should be using a limit on the number of sigmas. So we don't get those huge tails that come out at 10 to the minus 7, 10 to the minus 8 that basically nobody could ever design for.
Okay. We have looked, as have other people at John Anderson at Reno, Nevada, at the largest recorded motions and tried to find systematic reasons why they appear, and that still eludes us. Certainly they don't necessarily stand out as the highest epsilon values or small epsilon values. They don't give us an insight of where we could truncate the distribution. Clearly, if we conduct PSHA without any truncation at all, at very low annual frequencies of exceedance, we will generate ground motions, which many people would question if they could be physically realizable. And that's exactly what has come out of the post-mortem, if you like, on the Yucca Mountain PSHA and I think it's $5 million DOE project of trying to extreme ground motion workshop, which is looking exactly for physical constraints on the ground motions. But I don't think that has to be put in after. In terms of the damage, if possible, influence of the ground motion, that would be dangerous for us to take it out on the ground motion side. At the moment, a hazard analysis is only trying to represent nature. The engineering implications have to be handled elsewhere. I personally believe that Paolo Basura's work on vector prediction is going to give us a lot of handle on how to eliminate motions which are not really contributing to the damage. But that's some way off, I think, from widespread implementation yet.
Last question.
Hi, thank you for your presentation. Could you go to the slide that you show the epistemic uncertainties for different magnitudes, 5, 6, and I think 8?
Okay, go on to this one. Whoop, where am I'm not sure exactly which one you're referring
So
to.
there was a slide that you showed by magnitude how the epistemic uncertainty changes, and you mentioned that for magnitude
For the
6,
NGA equation.
yes, and you mentioned that for magnitude 6, since you have more data, the epistemic uncertainty is smaller than magnitudes 5 and 8.
Yeah, okay, I think that's what you're talking
Yes,
about. Yes,
exactly.
Okay.
My question is that, yes, I understand your comment on why the epistemic uncertainty in magnitude 6 should be smaller based on the amount of data. But if you look at the USERF2 document, around that magnitude 6 is exactly where the USGS model, in a way, if you will, in two strong terms, fails. And you have that bulging effect that kind of crosses the data. So
I don't know what you're referring to.
Yeah, it's different.
Oh, okay, okay.
yeah, so the recurrence rate, if you follow the USGS logic tree, is actually is failing on magnitude 6. So in a way, you should even have a larger epistemic uncertainty around magnitude 6, if anything.
But not here. Not here, because remember, the magnitude that goes into a ground motion equation in a PSHA is perfectly known. There's no epistemic uncertainty on the magnitude, because we're running calculation for scenarios. What if, we're asking the question, what if all these earthquakes were to occur?
But I thought you're using USGS logic tree, and then the attenuation functions is the last
Yes, but
branch.
your question, if I understand you correctly, you're talking about epistemic, you should think there should be larger epistemic uncertainty in the source characterization model.
Yes.
Fine, so they need to change that part of the logic tree. That has no impact on the epistemic uncertainty in the ground motion prediction.
Okay.
On the hazard.
Yes, exactly.
But this isn't hazard. This is a ground motion prediction.
Okay.
The magnitudes are the same which go into these different modes here. So they are closer there where the data is denser.
Yeah. It doesn't affect, doesn't.
Yeah, attenuation.
Great. Thanks.
Again, thank you very much for very, very interesting and informative presentation. So Julian basically went through all the fundamentals, and now